Hi guys, so this lesson is about volumes of revolution. So we're going to start with the bones of our equation. Anytime we're doing a volume of revolution, we are always going to set up volume equals. Make sure you write out the word volume. And then you're going to have pi, that's a constant that's always going to go out in front anytime you're revolving any sort of function. And you're going to go from a to b of something squared minus something else squared. And I always recommend starting with this. So that you have the bones of the equation. So the parentheses squared minus the parentheses squared. It's really easy to forget a minus sign or a squared or something. In this first equation, you're going to have your R out, which stands for your outer radius. And I'll explain what that means in a second. So you're going to have your outer radius, and then you're going to subtract the squared of your R in, which is your inner radius. So we're going to be able to determine what those things are depending on the equation we have. We started this one in class, but I'm going to go ahead and start it over just so that we can all be on the same page. So this problem says, find the volume of the solid that results when the area bounded by y equals 2x and y equals x squared is revolved about, and then we have the x-axis. So we're taking this and revolving it about the x-axis. So what I always recommend doing first is drawing a picture of our graphs. So I have my x and my y-axis. I have y equals x squared. Doesn't have to be a perfect graph, but it generally helps to just have something on there drawn. And then we have y equals 2x, so that's a line like this. Okay, again, my graph's not perfect, but it's good enough. Well, it doesn't give us the bounds for that area, so we're talking about this area bounded by, so that's this area right here that we're talking about, and what we want to do is we want to revolve that area. But we need to find what the bounds of that area are, so we need to find these x places where those two graphs intersect. So in order to do that, you have to set the two equations equal to each other. So we're going to write 2x is equal to x squared. You have to show this works. Sometimes this is worth its own separate point. Sometimes it's just necessary in order to get points on the FRQ. So we have 2x is equal to x squared. We're going to subtract the 2x. So we get x squared minus 2x. That would be equal to 0. We can factor out the x minus 2 times x, and then we get x equals 0 and x equals 2. So those are our intersection points, where x is equal to 0 and where x is equal to 2. Okay, now we're going to write the bones of our equation. So just like I said before, we're going to have volume equals, we're going to have pi times an integral of something squared minus something squared, and then in this case dx. And I'm just going to erase part of this so I have room. Oops. See if we can just move this down a little bit. And we get a dx there. Sorry, that's kind of crowded looking. So the thing that's going to go on our integral for our bounds are our intersection points that we just found. So we're going to go from 0 to 2. That's what's going to go on our bounds, are those two intersection points that we found. Okay. Now the thing that goes in our first parentheses is our R out. Okay, that's what's going to go here, is whatever our outer radius is. The thing that's going to go in our second parentheses is our R in, whatever our inner radius is. So this is a little bit challenging to think about, but the method that tends to work best for most students is to put a dot on the thing you're rotating it about. So in this case, we're trying to rotate it about the x-axis. So I'm going to put a dot on the x-axis with my pencil or pen or whatever you're using on your paper. And then I'm going to draw from that dot to the farthest part of the function. And I don't mean up here the farthest part. I mean, I guess the farthest curve. I want to see the distance between the place I'm rotating it about and the farthest away curve. So no matter where I am, that yellow curve is always the one that's farthest away from the x-axis. Okay, I'm not specifically talking about a y value. The distance between that yellow curve and the x-axis is variable. So I should have a variable in my R out, my outer radius. It should be an amount that varies. And so what I get for that amount is the distance from the x-axis to the curve of 2x, which in this case is just 2x. That would be that distance covered there. That's my outer radius. I'm going to do the same thing, but with my inner radius. So I'm going to start on the thing I'm rotating it about, in this case, the x-axis, and then I'm going to draw it to the closest curve to that point of rotation. So the closest curve here is our y equals x squared curve. And again, we wouldn't just say like at 4 or 0. We're not talking about a specific value. We're saying all along that interval from 0 to 2, what's the closest curve to the x-axis? And the closest curve, or our inner radius, would be x squared. For this question, I said set up but do not evaluate, so this would be it. This would be your final answer. You've got volume equals, you've got pi times, the bounds are included, you have your outer radius squared minus your inner radius squared. One important thing, and a thing that students mess up often, this would be wrong, don't write this, but I see some guys do pi times the integral from 0 to 2, and they'll do 2x minus x squared and then the whole thing squared. That's incorrect. That is not the same thing, right? It's not the same to distribute that squared here. So make sure you have it separately as your r out squared minus your r in squared, and again times pi with your bounds. Okay, so that's what we would get if we rotated around the x-axis. Let's look if we rotated around other points or other lines. Okay, so this time we're going to take that same curve, so we're still on that same graph, so I'll draw that again. We have the graph of, try to be consistent with my colors, the blue one was the parabola. So we have this parabola here, that's our x squared graph, and then we have a line, that's our y equals 2x graph, and we already know our intersection points, we already found them in that first part, should be at 0 and over here at 2. Okay, but this time we're rotating it about the line y equals -1. On the last one we rotated about the x-axis. This time we're rotating about the line y equals -1. So my graph's not perfectly to scale, doesn't really matter. This is now the line y equals -1. That's the thing we're rotating it about. We're going to set up the bones of our equation just like we did on the last one. So we have volume is equal to pi times the integral of something squared minus something squared. And it's not always going to be dx, and we're going to talk about why that changes. But in this case, it is still dx. Essentially, anytime you're rotating it this way, you get a dx. And anytime you're rotating it this way, you get a dy. Okay, but everything in your equation has to be in terms of x if it's a dx, meaning your bounds and the functions have to have x's in them. And then everything has to be in terms of y if you're rotating it this way. If you get a dy, that means your bounds are going to be in terms of y and your equations are going to be in terms of y. Okay, so since we are still rotating it this way, I'm taking that little slice of a curve and I'm rotating it about y equals -1. Since my rotation is still this way, we still have a dx equation. Okay, this time, again, the bounds are the same, 0 and 2. We already found that. That's not changing here, because that's an x equals 0 and an x equals 2. But my outer radius and my inner radius change. So I'm going to put my pencil or my pen or whatever on the thing I'm rotating it about. This time it's now y equals -1. And I'm going to draw it to the farthest curve away from the thing I'm rotating it about. Okay, now this is where this gets confusing. To go from the yellow line to the x-axis, so just this portion right here is y equals 2x. That's how long it is to go from the curve to the x-axis. That's that distance. But I'm not just going that far now. Now I'm going that distance and an additional 1. I've made it longer. So 2x is just the distance from that line, that yellow line, to the x-axis, but I'm extending it by an additional 1. I'm making it even longer, meaning now my outer radius is going to be 2x plus 1. That's the entire distance of that outer radius. My inner radius, we're going to do a similar thing. We're going to draw it from the thing we're rotating to the closest curve. Now again, the distance from the blue curve to the x-axis, that distance from here to here is a distance of x squared. That's how far that is. but we have an additional distance. We're making it even longer. So we're adding an additional 1 to that. And so that gets me x squared plus 1. That would be my inner radius. So we're always going to put it on the thing we're rotating it about. We're trying to determine what is the length of that radius from the thing I'm rotating to the farthest curve, and then from the thing I'm rotating to the closest curve. Again, we're just doing setup but do not evaluate. If it asks you to actually solve, you'd have to FOIL these out, simplify, take the integral, plug in your bounds, and solve from there. But this is usually worth the majority of the points, so making sure you have the setup correct is most important. Okay, let's rotate around another thing. So now we're going to rotate around y equals 7. Let me go ahead and draw this again. Same sets of curves. We have the y equals x squared graph, and we have the y equals 2x graph. That's here, okay? And maybe go ahead and move this down a little bit. This time it's asking us to rotate it around y equals 7. So y equals 7 is going to be above, right? So I have something, I don't know, way up here. This could be y equals 7. It's not really probably to scale or tall enough, but it's fine. Again, we had our points of intersection. Those were down here. We're going to set up the bones of our equation. So the bones of our equation is volume equals pi times the integral of something squared minus something squared. Now, I'm rotating it around y equals 7. So this time I'm rotating it up instead of rotating it down, but I'm still rotating it this way. So anytime you're rotating it this way, that is a dx. So I'm going to have a dx here. My bounds have not changed, so I'm still going from the bounds 0 to 2. Those are in terms of x. So from x equals 0 to x equals 2, since we have a dx, everything has to be in terms of x. Okay, these are the ones where students really struggle when it's above generally, or left or right can also be complicated. So again, I'm going to start with the thing, my pencil on the thing I'm rotating it about. So we're going to start with our pencil on y equals 7, and we're going to draw to the farthest away curve. So the farthest away curve is now the blue curve, but it's a little challenging to think about what that distance is. So here is how I suggest thinking about this. The distance from that curve, so from that blue line, or from the blue parabola, excuse me, to the x-axis, that distance is x squared, which we just talked about in the last one. So the distance from the curve to the x-axis is x squared. The distance from the top of that to the x-axis is 7. So that total distance is 7. The distance from the parabola to the x-axis is x squared. So I'm looking for the difference of those things. So what I end up getting is 7 minus x squared. Right? That would be that distance here, would be the distance between those two things. Okay? Again, that's to the blue curve there. So 7 is the total distance. X squared is the distance to the x-axis. The length of my outer radius, so from the thing I'm rotating it about to the farthest away function, would be 7 minus x squared. Okay, we're going to do a similar thing with our inner radius. So our inner radius, again, put my pencil on the thing I'm rotating it about, draw it to the closest curve, not the closest point, to the closest curve. And so that case, we are drawing to the yellow. Well, the distance from the yellow line to the x-axis, this distance here is just 2x. So I have a distance of 2x there. The total distance is 7. So we end up getting 7. Oops, what happened to my 7 minus x squared? Sorry if I erase that. 7 minus x squared. And then we get 7 minus 2x. So you'll notice the order is different, right? On the previous one, on the first one, we had 2x by itself and then x squared just around the x-axis. Then we had 2x plus 1, or x squared plus 1. Now we have a 7 minus. Again, the total distance is 7. And then we have the distance from each curve to the x-axis. But they're also in a different order. Like now the x squared is the one that's part of the r out versus the 2x being one that's part of the r out. So it can change. It's really important that you actually draw that picture and think about which one is the furthest away. Okay, now we're going to do it slightly different. We're going to do it with respect to the y-axis. This can also be very challenging for students. We have the same picture drawn. Okay, so I have my y equals x squared curve. This is y equals x squared. And then we have our y equals 2x curve. So the blue one, or excuse me, the yellow one is y equals 2x. And we already know that they intersect here and here, which is where x equals 0 and where x equals 2. We solved for that on the first one. Here's what's challenging about this one. Now we are rotating it about the y-axis, okay? We'll never rotate it about something that cuts through the region, by the way. Some students are worried that that's going to happen. Not in Calc AB, at least. We're not going to rotate around something that cuts through the center of the region. So it's allowed to touch the region, but it's not allowed to cut the region. And so we're rotating it about the y-axis, which means we're rotating it this way this time. We're rotating it like this, meaning we're going to have a dy equation. So now my bones are set up slightly different. We have volume equals pi times the integral of something squared minus something squared, but now it's going to be dy since I'm rotating it this way. Okay, a few other things change as well. It would now be wrong to put the bounds as 0 and 2 because those are our x bounds. So we had x equals 0 and x equals 2, but now we want those bounds in terms of y. So we just have to think about what those bounds are in terms of y, and because those equations intersect there, they have the same x and y coordinates at each of those places. So here, for example, the x and the y coordinates are both 0, but you could figure that out by plugging in 0 to either equation. So I could get y equals 2 times 0, or I could do y equals 0 squared. They're both going to produce the same y coordinate. It's going to be the y coordinate of 0. That corresponds to this one. So that's maybe confusing because it's the same as the x coordinate. Maybe makes more sense when you look at the next one. So here we had an x coordinate of 2, but I don't care about the x coordinate. We care about the y coordinate, and I can find what that coordinate is by plugging 2 into either the blue or the yellow equation. So we could do 2 squared or we could do 2 times 2. They have to be the same y value because they intersect, and we get 4. So our bounds have now changed. Because we're doing it with respect to y, my bounds are also in terms of y, okay? Before we start thinking about r out and r in, we also need our equations to be in terms of y. So before we had stuff like x squared or 2x, stuff that had x's in it. Now what we need to do is change it so it's in terms of y. And to do that, all we do is instead of isolating y, we isolate x. So for example, the blue curve, if I were to isolate the x, I would get x equals the square root of y. And it's not plus or minus, it would just be the plus in this case, because you can tell for this region up here, y is always positive. So it would just be the positive square root. So we have x equals the square root of y, or y to the 1/2 if you're solving it and that feels easier. I'm just going to call it x equals square root of y. So that's the one we'll actually use for this curve. We won't use y equals x squared because we need everything in terms of y. For the yellow one, we're going to do the same thing. So we're going to leave this in terms of x. We're going to get x equals y over 2. So this is going to be the actual equation we use when we're in terms of y for the line. The line is going to be x equals y over 2. Okay, now the process is very similar. Since I'm rotating it about the y-axis, I put my pencil on the y-axis and I draw to the furthest away curve. So the furthest away curve here means I'm connecting it to the blue curve. Okay, and now the distance, instead of the distance being from the curve to the x-axis, since we already have it in terms of y, it is the distance between the curve and the y-axis. So that distance to that blue curve is the square root of y. That would be that distance. The distance from the y-axis to the blue curve is the square root of y. We'll do the same thing with the other curve, which is a line, right? We go from the thing we're rotating it about to the closer curve, and in this case, that is the line, and the line is y over 2. So it's no longer called 2x. Because we're in terms of y, everything has to be in terms of y. Meaning the bounds have to be in terms of y, we need a dy at the end, and we need all of our equations in terms of y. So we got square root of y, quantity squared, minus y over 2, quantity squared. Again, this is just set up but do not evaluate, so we don't have additional answers from here. But obviously, if you were asked to solve it, you would square both of those terms, take the antiderivative, plug in the values, right? Plug in the top bound, into each of those things, subtract plugging in the bottom bound, and then don't forget to include your pi at the end. Okay, we're going to do, I think, 2 more examples. We're going to have an example where x is equal to 3. So same curves. So again, I'll draw this. I should have probably just copied this a couple times. Wasn't thinking. So we have our y equals x squared, but it might be actually helpful for you guys to draw this each time so that you are making sure you're copying down like where we're taking that line from, so you can see like where our outer radius and our inner radius is. Okay, so we have those 2 curves. I'm not even going to name this as a y equals this time. We're just going to keep it in terms of y. So our blue curve is x equals square root of y, and we said our yellow curve is x equals y over 2. Again, since I'm rotating it about x equals 3, let me maybe throw these somewhere else since we're rotating it over there on the right hand side. So we had x equals y over 2 and x equals the square root of y. Okay, now we're rotating it still this way. So x equals 3 is the thing we're rotating it about x equals 3. Well, this is x equals 2 right here, so x equals 3 is a little bit further. So I'll just draw that right here. So this is x equals 3. That's the thing I'm rotating it about. Okay, so to go to x equals 3, again, I'm going to put my pencil or pen or marker or whatever on the thing I'm rotating it about. Oh, let me set up my bones really quick so we don't forget to do that. So volume equals pi. Don't forget that pi. It's very easy to forget. Integral of something squared minus something squared, and then again dy. Since I'm rotating it this way, this needs to be a dy. My bounds, we just found those and talked about that. My bounds, instead of being 0 to 2, they're going to be 0 to 4 because they're in terms of y. Okay, now I'm going to put my pencil on the thing I'm rotating it about. That's x equals 3. Draw to the furthest curve away. So I get this distance to that yellow curve. Okay. So we have to be careful about this one because the distance from the y-axis to the yellow curve, this distance here is y over 2. That would be this distance, y over 2. The total distance to the thing I'm rotating it about would be a total of 3. So I want the difference between those 2 things. So the difference between those 2 would be 3 minus y over 2. Okay, that's going to go in our r out. Again, we started with the furthest thing away from the place I'm rotating. Then we're going to go to the closest thing. So again, I'll put my pencil on the thing I'm rotating it about. Go to the closest curve. Now we have to keep in mind the distance from the y-axis to this curve. So to the blue curve, that distance is the square root of y, and the total distance is 3. So what we end up with here is 3 minus the square root of y. Okay, and again, that would be your setup, but do not evaluate. One more. Now we're going to rotate it around x equals -5. These are kind of all of the different options. So x or y axis, above or below, or to the left or to the right of the curve. That's kind of what we're dealing with here, and all of the different options you're likely to see on the AP exam. Okay, so again, I have my parabola. Again, my parabola is called x equals the square root of y in this case. You don't technically need that whole parabola if you're wondering. Like, technically, it is just this portion over here that we're using. So if you just drew that, that's fine. I'm just in the habit of drawing the whole thing, so do you. So we have this over here. Actually, just because it's to the left, maybe I'll keep it over here. We just really need the region that's we're rotating it about. So x equals square root of y. Then we have our line, and our line went like this. And again, that line, we don't need the whole thing, we just need the region that we're including, but that equation is x equals y over 2. We're going to set up the bones of our equation. So the bones of our equation is volume is equal to pi times the integral of something squared minus something squared, and then again dy. I know my bounds are going to go from 0 to 4. Again, the reason it's dy is because I'm rotating it this way. The thing I'm rotating it about is x equals -5. So x equals -5 is somewhere over here. this would be x is equal to -5. Okay, now we have to fill in our r out and our r in. So our r out, we take it from the thing we're rotating it about, which is x equals -5, and we draw it to the furthest away curve. So the furthest away curve is all the way to this blue curve. Now the distance from the blue curve to the y-axis is square root of y, but we are lengthening that. We are going an additional 5. Sometimes people get confused because there's a -5 there, but that total radius is becoming much longer, right? This distance from here to here is just square root of y. I am lengthening that quite a bit. I'm not subtracting from it at all. I'm just adding to it. So what I'm going to get there is I'm going to get the square root of y plus 5, or 5 plus the square root of y. The order doesn't really matter there. Okay, and then we're going to do a similar thing, but we're going to look at our inner radius. The inner radius, again, we start with the thing we're rotating it about. So we start with our dot at x equals -5, and then we go to the closer part of the function. The closer part is now the linear function here. Again, the distance from the y-axis to that function, the distance from here to here, is y over 2. That would be that distance. And I'm going an additional 5 on top of that. Like I'm adding 5 to that entire radius, which is where I get y over 2 plus 5. Okay, so that's the basics for how we're going to do all of our volumes of revolution. We're always going to figure out if we were doing a dx or a dy equation, write the bones of our equation. So that's pi times the integral of something squared minus something squared. Make sure you have those parentheses, squareds, and subtraction. You're going to draw the curve. You're going to draw the thing you're rotating it about. And then you're going to draw the how far it is from the thing you're rotating it about to the farthest away curve, the thing you're rotating about to the closest curve. Make sure you also find your points of intersection and then write those either in terms of x or y, depending on what you are rotating it about. Again, if I'm rotating it this way, it's a dx. If I'm rotating it this way, it's a dy. Okay, that's all I have for you. Have a great day. Good luck.